We're going to end this section with a quick comment about the Millenium Bridge. So now the Millenium Bridge, as you can see here in the textbook, is a bridge that was first opened in, let's see, it was in June 2000, but there was a lot of horizontal oscillations, and that was a bit surprising to people for a couple of different reasons. And what happened, and if I can pull it up for you a little bit, I'll link this as well. What happened is, as a bunch of people were walking, you got these horizontal oscillations. The bridge was really going from side to side. Now, this is a little bit surprising to a lot of people, but what kind of led to that is that the bridge had a large amplitude response to the horizontal forcing. Specifically, there's a forcing of about 1 cycle per second, which is related to the natural speed that a lot of people walked. Now, normally that wouldn't really matter too much. Normally it wouldn't really matter because people are going to be walking at all different times, slightly different paces. And, when I take a step's not necessarily when you take a step. However, it turns out that somebody took a video, well, we just saw one such video, and you could actually see that a lot of people were marching in time. And it's just kind of the way that when we have high levels of congestion, people do tend to naturally line up their steps, or so it would seem. I am not an expert on this. Just naturally, like they're not trying to do it. They're not trying to swing the bridge, or maybe in this video they are, but certainly this didn't originally happen naturally, or it did happen naturally. It wasn't originally forced. And there's a lot of cool videos. I'll probably link some of them that talk about this phenomenon. But yeah, a video you'll see that people just tend to walk in step. And that led to the forcing frequency being very close to the natural frequency, at least in the horizontal direction. Specifically, we're talking about horizontal forcing here. And so it was kind of swinging side to side, which is pretty interesting. And again, there is damping here, right? This is not a perfect bridge with no damping, right? So the section that we just talked about is really only about forced harmonic oscillators, undamped harmonic oscillators. But as we'll talk about in the next section, even if there's not very much damping, or if the damping is small in comparison, right, because it's all relative, then things can really behave very similar. We can see models kind of approach that theoretical like perfection that's never going to happen. We're never going to have no damping, for example, but we're still going to be able to see that behavior manifest in situations that are very close. So we'll be varying some parameters with the natural frequency and the damping, the forced frequency and the damping. We're going to see how that affects some things as well. And that's what we're doing in the next section. So we'll mostly just, I think, one other comment I wanted to make is that we've done these models so frequently, right? How many times have you seen me write this down? My double dot plus b times y dot plus k times y equals, we've done this so many times. This is a linear approximation, by the way. This is saying, okay, the damping force is proportional to the velocity. The spring constant is proportional to the position. And those are very good things to say. But this is a linear approximation. And linear approximations are great. We're really mostly only dealing with linear approximations in this class. Linear approximations are really, really great, but they are just approximations. We can get better models of harmonic oscillators as well. We'll use nonlinear models. And in this class, we don't talk about nonlinear differential equations, but that's certainly something that is talked about a lot. It's certainly much more complicated, which is why we're not covering it in this section. But that is something that happens. So watch out. Linear models are great for kind of local conditions or certain nice situations. But if your load is too big or if the initial condition is too large, you're going to need like a more precise thing. You're going to need a nonlinear differential equation to model this. So the last thing I want to leave you with is this section on resonance is if you have an undamped or maybe a very tinily damped harmonic oscillator, you can have resonance happen if your natural frequency gets close to your forcing frequency, right? If this is some kind of sinusoidal function on the right, could be cosine, could be sine. If the frequency here matches up with the frequency that you get from the eigenvalues from that natural response, then you're going to have resonance and you're going to have some crazy things happen. Think somebody swinging on a swing set. Think a spring getting like oscillated just right to make it really go up and down. Think somebody singing and shattering glass, all things that can happen with resonance. And that can be dangerous, as in the case of bridges, but it can also be powerful. We can also use resonance to our advantage. If you're thinking of like amplifying a radio signal or something, a radio wave, we want to amplify the radio wave, we can do that using resonance. And there's plenty of other examples out there as well of ways that we can use resonance to our benefit. So it's something that we should be aware of because it can be dangerous, but it's something also that we can use to help us. And that's why we study it here in this class. We have one more section on forced harmonic oscillators, and then we'll move on to chapter 6, where we talk about the Laplace transform. What happens if we have discontinuities on this right-hand side, which will happen very frequently if we have something like flicking on a switch. Anyway, we'll get there when we get there, but for now, just enjoy where we are. Have a good rest of your day, and let me know if you have any questions. Bye-bye.